നോക്കുന്നില്ലെങ്കിൽ ഇത് സാർ ഒന്നായിട്ട് ഫോർവേഡ് ചെയ്ത് കൊടുത്താലും മതി.
ശരി, ഓക്കെ.
നിങ്ങളാണോ ഇത് പ്രസന്റ് ചെയ്യുന്നത്, ബാബുപ്പിയാണോ പ്രസന്റ് ചെയ്യുന്നത്? ഓക്കെ, ഇന്ന് ബാബുപ്പിനെ വിളിക്കാം. മറ്റേ റോഷൻ അങ്ങോട്ട് കയറിയിട്ടില്ല, എന്തോ പ്രശ്നമുണ്ട്. വിളിക്കാം. അത് സ്റ്റോപ്പ് ആയില്ലേട്ടാ, റോഷൻ കയറിയിട്ടില്ല, എന്തോ ഒരു പ്രശ്നം വന്നിട്ടുണ്ട്. ഇല്ല, മൂപ്പർക്ക് കയറാൻ പറ്റുന്നില്ല പറഞ്ഞ. അപ്പോൾ പറഞ്ഞിട്ട് സ്റ്റോപ്പ് ചെയ്താൽ മതി.
Hello. Am I audible?
Yeah, 1 minute, Shibin. Hello.
റോഷൻ ഇപ്പോൾ വന്നിട്ടുണ്ട്, അഡ്മിറ്റ് ആയി.
Shibin, you're audible.
Okay. Let us begin in the name of the Almighty, the most gracious, the most merciful. With His blessings, I wish a very good morning to one and all. We all are passing through tough times, and may the Almighty ease the testings and help us recover mentally, socially, and economically. I welcome current outlook of civil engineering 2020 COC 20 organized by the Department of Civil Engineering, MEC Kuttipuram, from 16th to 20th of November 2020. This National League Conference aims to provide an opportunity for academicians, technologists, entrepreneurs, students, and other members of the engineering community to put forward their ideas and findings related to recent trends in the area of civil engineering. We will begin the day's deliberation.
A very good morning to one and all. It's a matter of pride and pleasure for me to welcome Dr. Roshan Khan, who was my student during both his BTech and MTech course. Being a very hardworking and meticulous person, the seminars, project work, and all the works which he did, which he took up, were very innovative, and he received many awards for his project work, which later led him to join for PhD at IIT Bombay. And his brilliant performance during his PhD and later are a matter of inspiration for everyone, and especially so for students from self-financing colleges. He also got selected to the research associate position in the University of Cambridge, but he could not go due to the international travel restrictions caused by the pandemic. We are fortunate to have him with us for delivering the keynote address on a topic of significant relevance. On behalf of the Department of Civil Engineering, Mes College of Engineering, Kuttipuram, I would like to welcome Dr.M Roshan Khan for the keynote presentation in the National E-Conference on Current Outlook of Civil Engineering. I would also like to welcome our principal, Dr. A.S. Varadarajan, members of the Conference Advisory Committee, heads of departments, faculty and staff members, delegates, students, and friends for today's proceedings. Now, for the smooth conduct of the lecture, I would like everyone to abide by the following guidelines. Attendees are requested to mute their mic and turn off their camera. Please do not present your screen in between. Questions are to be posted in the chat box. The organizing team will present the questions to the speaker at the end of the session. The speaker will answer all the questions if the time permits. online webinar record in YouTube. If you need any assistance during the program, please use the chat box. Now I'd like Ms. Agrima M to introduce the speaker to the audience. Thank you.
Good morning, all. It is my pleasure and honor to introduce the keynote speaker of the day, Dr. M. Roshan Khan. Dr. Roshan Khan is a PhD graduate in civil engineering from IIT Bombay, and currently he is working as a project research associate in the Department of Civil Engineering at IIT Bombay. His research interests lie in the areas of railway geotechnics, soil dynamics, and numerical modeling in geotechnics. Dr. Roshan's doctoral research was on the characterization and mitigation of ground-borne railway vibrations. He has completed his professional education in railway engineering from the Delft University of Technology, the Netherlands in 2019 on the train track interactions, real-time railway operations, and long-term performance of railway infrastructure. He is an author of 20 research papers in international journals, special publications of journals, and international conferences of repute. He also serves as a reviewer in the major international journals like Transportation Geotechnics Elsevier, Transportation Infrastructure Geotechnology Springer, and Vehicle System Dynamics Taylor and Francis. Dr. Roshan is also a recipient of the prestigious IGS ISAT Award from the Indian Geotechnical Society for the Best Master's Research Thesis produced in Kerala in 2012-2013. And he has also received Excellence Awards, Best Paper Awards, and Best Presentation Awards in national and international technical conferences. Through this lecture, Dr. Roshan will briefly present the geodynamic aspects and environmental impacts of high-speed railway operations. So welcome, sir. I request you to address the gathering.
Very good morning to everyone gathering. And I would like to thank the organizers of this e-conference for giving me this opportunity to deliver a keynote lecture. And in fact, I am really happy that I'm able to deliver a lecture in this conference because my association with Professor Syed Jalaluddin Shah dates back to almost 15 years when I was a BTech student. And I was really fortunate that Professor Syed Jalaluddin Shah was my BTech guide. And after that, he was my MTech guide. And I was also fortunate to work with him as an assistant professor when he served as the HOD of the department. So it's really a pleasure for me to deliver this lecture in this conference. And I would also take this opportunity to wish all the best to the presenters in this conference. And I hope that it will be a very useful learning session to all. And without sparing much time, I'll begin my lecture. So today I'll be speaking about the geodynamics of high-speed railways. So as you might be knowing, Indian Railways is having extensive progressive plans to construct high-speed railways in India. So the thing is, the railways in India, the Indian Railways was founded by Britishers. So at those times, the importance was on carrying heavy freight across the country. So it was not on the speeds, but at this time, the people had to carry heavy freight like the materials from the coal mines, from the steel plants, etc. So at that time, the preference was given to the carriage of heavy freight instead of the speed. So what happened is at those times, the Britishers laid the tracks with the broad gauge spacing. So broad gauge spacing basically means the space between the two rails, and broad gauge means the spacing is 1.67 meters. So this was basically given because when the spacing is higher, the railway track is able to take higher loads since the load will be distributed to a wider space. So at that time, we had broad gauge spacing, and still in India, we are following the broad gauge spacing. But having this broad gauge rails comes with a plethora of its own problems, especially when we are considering higher speeds of train operations. So the first problem what we would encounter is when a train is passing through a broad gauge track, there are a lot of drag forces associated. And in order for the passage of the train, it requires more locomotive power. And it also becomes difficult when a train has to take curves or gradients throughout the railway track. So all these lead to the factor that we won't be able to achieve higher speeds in the broad gauge tracks. So that's why if you see mountain areas and places like that, in those places we can see that the tracks are mostly laid in narrow or say meter gauges because it is easier for the train to pass through them. So we as civil engineers have new lands for the construction of the railway track, and also it will take a lot of time for constructing new tracks. So that was the first option. And the second option comes when we want to utilize the existing tracks to their maximum capacity. So this is where my project begins. So instead of constructing new tracks, how we can utilize the existing tracks to the maximum capacity. That's what I have focused on my research. So I'll just begin my presentation now. So is the screen visible?
Yeah, it's clear.
Okay. Yeah. So this is my project. This is in what I have been working for the past 5 years. We'll be dealing with the geodynamics of high-speed railways. I'm affiliated to the Department of Civil Engineering at IIT Bombay, and you can contact me in this email address if you have any queries. You can note it down. So we'll just begin with this session. So I'll just introduce you to what the geodynamics of high-speed railways are. Especially in the urban railway networks, what we can see is that a lot of inhabitation is close to the railway tracks. So whenever you're waiting on a railway platform, you can see that still in India we are following the vertical spacing. But as a train reaches a railway station, we start feeling the vibrations. So these vibrations actually travel from the train through the ground, and then it comes to the receiver. That is, when we are waiting on a platform, we are able to feel the vibrations because the vibrations in the train pass from the ground, and then we receive those vibrations. So the objective of this study or my work is to reduce these vibrations from propagating away from the track. So if we want to conduct a study like this, we can basically divide the problem into 3 parts. The first part, we have to find out what is the load which is being transferred from the train onto the track. So this forms the first phase. And by meaning the force, we have to find out what are the normal forces acting and what is the friction acting between the train and the rails. And in the second phase, what we have is, once we know what is the load which is being transferred from the train onto the track, we will be estimating what are the vibrations created due to these loads being transferred from the train. And in the third phase, we can see that these vibrations are being transferred from the railway track onto a surrounding building. So we will be introducing a barrier between this so that the vibrations won't be reaching these sensitive structures close to the railway tracks. That is our aim. So throughout this lecture, I'll be mentioning about all these 3 parts. The first part is transfer of the load from train. Second part is the generation of the vibrations. And the third part is how to stop these vibrations from reaching a sensitive structure. So so it is known that the vibrations will be higher when the train is getting more vibrations onto the ground. And also when the trains are longer, the period of travel will be higher on the track. And then again, the vibration generated will be higher. So in this study, what we are trying to find out is what will be the difference or what would be the impact when the speed of a train changes. So that's what we are studying in this particular research. And the right side figure shows a general particle movement profile. So whenever vibrations come, imagine that this red spot is a particle in the soil. So whenever vibrations come, the soil particle in the ground moves up and down. So that is how the vibrations are being felt in the ground. And these vibrations travel from the railway track onto the surrounding structures. So it is not easy to conduct full-scale studies in the field because whenever we are conducting studies in the field, it's very difficult to have trains running in the same speed and trains running with the same axle load. So we won't be able to get correlations when we are doing studies in the field. It might be very case specific. So in order to address that, what we are trying to do is we are trying to model this railway travel in a software called Abacus. It's a finite element analysis software. And in this software, we are trying to find out how these vibrations are being generated by the high-speed train. And as you know, the modeling of the railway track systems can considerably reduce the costs as well. So if you're considering a test in the field, say it will take a lot of money, it will take a lot of time. So instead of that, if you want to model, say, n number of tests, n number of railway passages, you can do that in a software easily. But you need to validate the software first. So whenever you're doing a numerical modeling test, or whenever you're trying to model something in the computer, first you have to validate whether your model is working properly. So that is the first challenge when you're doing. So once we are finding out the vibration levels, after that we are trying to find out how we can reduce these vibrations. That will be the final part of the
യൂട്യൂബിൽ
study.
ശരിയായിട്ടുണ്ടല്ലോ, right വന്നിട്ടുണ്ടല്ലോ.
So if you would go through the recent literature, what you can see is that there are two basic drawbacks in the studies currently being conducted on high-speed railway studies. So first of all, whenever we are modeling railway operations, the first thing is that we assume that the load from the wheels. So you can see that there are two rails and the wheels are passing over the wheels are rotating over the rails. And when these wheels are rotating, there is a vertical component in the downward direction and there is a frictional component in the horizontal direction. So whenever studies are being conducted, it is generally assumed that this vertical load is dominant and usually the frictional component is generally neglected. But from this study, what we found out is that even this friction also plays a major role to the vibrations being generated. So the first assumption what the general studies do is that they assume the train loads to be vertical point loads and then they assign a time history. But this is wrong. In spite of having the vertical load, we should also consider the horizontal traction stresses. And the second assumption what generally people do is they consider the railway track as a 2D problem. So by the railway track basically consists of the rails, and these rails are supported on sleepers, and these sleepers are supported on the railway embankment. And this railway embankment can be above the ground surface level or it can be with the ground surface level also. So after these rails, we have sleepers. Sleepers are supported on railway embankments, and this railway embankment is supported on the natural ground. So in this study, we will be finding out what are the ground vibrations in all these different layers. So whenever we are considering the railway track as a 2D problem, what happens is if you are saying about a railway track which stretches over kilometers, the railway track section will not be constant. So say, for example, if you're having the natural ground filled with sand at one place, say if you're going around 500 meters, the next place will also have sand and silt. The next place might have a layer of laterite. So in the site, if you're considering, you cannot simply assume that the railway track is a 2D problem. So whenever we are modeling, we have to consider the railway track as a 3D problem. So these problems were actually discussed by different researchers in different periods of time. So in the year 2006, Karlstrom had mentioned that whenever we are considering train wheels as vertical point loads, this basically neglects the rail friction. So that is the reason why we will need to use 3D models so that we can consider both vertical loads as well as we can input the frictional stresses on the rails. And then whenever we are considering the railway load as a 2D load,
ലൈവ്
or when we
യൂട്യൂബ്
are
ലൈവ്
considering
ഉണ്ട്,
as a
ഗൂഗിൾ
vertical
മീറ്റ് വേണേ
point load, and when we are considering 2D, what happens? A vertical
ഗ്രേസ്
load,
തന്നെ
a
ഫോർവേഡ്
vertical point
ചെയ്തോന്നുള്ളത്.
load, when we stretch it into a 3D plane, the vertical point load becomes a UDL. So, but in the reality, it's not a UDL, right? The vibrations are created when there is a wheel load. The wheel load passes and then the ground comes up. Again, there is a wheel load. The ground comes down. So there is an up and down movement of the ground, which will not be represented by a UDL. So that is another point. And then whenever we are modeling the train, this travels farther. With respect to the geometry, there is a geometric damping happening. So the vibration which is generated here is not the same vibration recorded at a place, say at 3 meters from this point. That is because of the geometrical expansion of the wavefront. So that will not be considered in a 2D model. So if we are particular about using 2D models, we can always make use of additional inputs like the traction stresses to be input in the 2D model. But again, if we have to consider the acceleration or the deceleration of a train, these become variables. So these traction stresses and the load values actually become variables in case of the acceleration or deceleration of a train. So all these are the different drawbacks of using 2D models or using vertical point loads as the railway load. So in our study, we are addressing both of these. First thing, we are considering the train loads as a contact pressure. So I'll be explaining about this. So as I mentioned, I'll just briefly summarize this. The first part of the study will be to find out the load transfer from the wheel onto the rail. In the second phase, we will be finding out the vibrations which are caused by these forces. And in the third phase, when we know the vibration levels, how we can mitigate these vibration levels. So one of the important factors what we need to consider is that in addition to finding out the peak particle velocities of the vibrations, it is also important to mention at what frequency these vibrations are occurring. So for that, we are also considering the frequency spectral analysis of the ground vibrations. I'll be mentioning about this in the later slides. Okay, so out of the three parts of the study, this is the first part. In the first part, we are trying to find out this software. And in this, in the right side figure, we can see that you can see a black patch here. This black patch is the contact stresses which we are which we are estimating. So if you're in the previous slide, I mentioned that in addition to the vertical load, we'll need to consider the friction in this contact patch. So what will happen if you're not considering this frictional stresses? Imagine that we are having a vertical point load, and when we are considering the passage of the wheel on the rails, the wheels will simply slide on top of this. If there is no friction, there is a vertical load, and if it is given a push here in this traveling direction, you can see that these wheels will simply slide without rotating. But in the field, if you see, the train wheels actually rotate, right? This rotation is caused by the friction at the wheel rail interface. This is the wheel rail interface. And so in this study, we will be estimating both the normal contact pressure, which is the vertical pressure acting in this vertical direction, as well as the traction stresses, which is the friction stresses acting in the horizontal direction. So if you imagine that the wheel is traveling in the forward direction, the friction stresses will be acting in the backward direction. So friction will be equal and opposite on the rails. So after carrying out the moving load simulations in this study, these are the results what we got. And in this graph, we can see the increase in the vertical contact pressure with respect to the train speeds. So we have analyzed a train speed from 160 kilometers per hour to 200 kilometers per hour. And the reason why we chose these train speeds is because the Indian Railways currently have trains with what happens when the train speed is pushed even beyond 160 kilometers per hour. So we're considering an increase in train speed by 25%, and we're considering how the contact forces are acting when there's an increase in train speed from 160 to 200 kilometers per hour. So in both these graphs, both the top graphs, you can see that both the contact pressure as well as the frictional stresses increase with respect to the train speed. And this is a quadratic increase, as you can see, but these both are not similar. So you can see that the vertical contact pressure is steeply increasing, and this is slightly steep. So the contact pressure increase is higher than the frictional stress increase, and this is actually represented by the third graph. So in this third graph, you can see that the wheel rail interface friction. So there is a friction occurring between the wheel and the rail, and normally for the steel interfaces, the interface friction coefficient value is 0.4. But in our study, what we found out is that the value doesn't stay at 0.4. So with the increase in train speed, what happens is the interface friction value starts reducing. So just imagine that in this case, the train speed will be higher. What happens is we will again have a drop in the interface frictional coefficient value. So this will start dropping. And at one point, maybe we will be losing the traction, so that the wheel won't be able to actually spin on the rails. So we should be always maintaining this value at an optimum value of 0.35, so that the train doesn't actually slip on the rails. So that is 135 is considered as an optimum value internationally. So from these three graphs, we are able to understand what is the load being transferred from the train onto the track. So this is the vertical three values, and these values become input in the second phase. So this is the second study, and in this phase, what we are doing is we are trying to model a 150-meter track length of the railway, and then we are trying to simulate the train travel from one edge of the model to the other edge, and we are trying to model this at different train speeds. So from this previous study, we know that what are the different train loads acting for different train speeds. So whenever we want to simulate different train traveling speeds in this model, we can simply assign the load value on top of the rails. So we don't have to again model a wheel and then again we don't have to run that on this. We can directly input the value of load as well as the friction occurring here, so that we'll be able to find out the ground vibrations. So the figure on top is actually the railway embankment section, which is specified by the Ministry of Railways in India. So this embankment section is designed for carriage of axle loads up to 32.5 tons. So this is the maximum axle load which is permitted, which is designed for operation in the Indian Railways currently. The maximum axle load is 32.5 tons, and these are the different stratas in the railway embankment. So on the top we have rails. Rails are supported on sleepers, and these sleepers are supported on the ballast. So when we are traveling by train, what we see is whenever we are taking out of the train, we see a ballast, right? We see the ballast, we see the sleeper, and then we see the rails. But beneath this ballast layer, there are different layers of earth which are being constructed. So this sub-ballast is supported by, the ballast layer is supported by a sub-ballast layer. The sub-ballast is supported on a subgrade, and this subgraded is supported on an embankment face. To the ground actually disperses to a farther position. So when we have to carry higher axle loads, we increase the embankment fill thickness. So since we are considering an maximum axle load of 32.5 tons, we have considered this section, this exact same section, and this railway embankment section is what you can see in the left portion, and then we have extruded this section to a length of 150 meters, so that we are able to simulate the moving load traveling on top of the rails. And the objective of developing this numerical model is to find out the vibrations which are generated during the passage of the train. So in the left side figure, we can see if this is the point, if the left side, the origin is considered as the point where there is an axle load passing. So from this point, there will be vibrations passing on top of the ground, as well as there will be vibrations passing beneath the ground surface level as well. So on the surface level, the vibrations will be maximum, and then there will be body waves passing through the ground as well. So we have to quantify both of these. And so this is the numerical model, or the numerical model of railway track developed using software Abacus. And these are the different material properties which we have assigned for different layers. So in this, on top we have the rail, and I have given in the same order in which we have modeled these layers. You can see that there are different layers in this. And one more thing is that this red portion is the analysis domain that we have. So we are quantifying data in this analysis domain. And this white colored outer portion is the infinite element domain. So I will speak more about infinite elements in the later slides. And these are the different material properties which we have assigned. So these are taken from these two references. So from in this, we have associative models like Drucker-Prager and Moore-Coulomb. And then we have assigned the properties like the Young's modulus, the Poisson's ratio, the density. And then for different, we have also considered different densities. So for different relative densities, all these properties will change. We are only considering sand here, but sand at different gradations and different densities. So here we are considering dense sand, we are considering medium dense sands, and for the corresponding values for the Young's modulus, the Poisson's ratio, and density is considered, and we are also considering the friction angle value as well as the dilation. And in the first figure, if you remember, we have seen a 150-meter track length. But when we considered analysis in this 150-meter track length, what we observed is that, imagine that for a passing train wheel at one location, the vibrations are actually propagating to a distance of 30 meters beneath the track, beneath the rail. So imagine that if there is a wheel standing at the center of the model, then the vibrations are significantly distributed in a longitudinal distance of 30 meters beneath the wheel, a longitudinal distance of 30 meters. So whenever we are doing numerical analysis, we have to optimize our model so that it is computationally efficient. So we reduce the size of this model so that we are able to only analyze the portion where there are vibrations, because in our study we are considering the vibrations generated by trains. So we are optimizing our model so that we don't have to run the entire analysis. We are only considered about the portion where there are vibrations. So you can see that this is a 30-meter track length, and then we are also considering plane symmetry at the track center line. So you can see that if you're taking a vertical section at the center of the track, then the left half and the right half are symmetric. So in the software Abacus, we have an option to assign a symmetric boundary so that, and the computation becomes faster. Since we have to run more than hundreds of analysis, time is a very big factor. And that's why we are optimizing our model for computation efficiency. So basically we are considering the first boundary condition is that there is a symmetry at the center. So there is half section of the track, and this symmetric section assumes that there is another half in this direction as well. And then in the second figure, you can see that the longitudinal boundaries of the model are restricted as well. So the restriction is that the soil cannot move in the longitudinal direction. So the soil can deform in the vertical direction. The soil can deform in the outward direction from the railway track, but not in the direction of train transit. So that is the second model boundary condition. And then the third thing is that I spoke about infinite elements. So this circular portion represents the infinite elements. So this is basically assigned in dynamic simulations when we are trying to simulate vibrations. So the purpose of an infinite element is to absorb the vibrations without reflection. So I'll just give an analogy for this. Just imagine that you're having a rubber ball in your hand, and if you throw it against a hard wall, the ball will bounce back, right? But if you're throwing it to a soft wall, the ball won't come back. Like it will hit the wall, and it will just fall down, right? So whenever we are having a stiff wall, if you throw something at it, it will come back with a higher speed. When it is soft, it won't come back. So these boundaries actually act as absorbing boundaries. So whenever a vibration is coming to this boundary, it doesn't go back, it doesn't reflect back. Because in the field, there is no boundary, right? In the field, this oil will be stretching too long. In the software Abacus, we have made use of element code CIN 3D8. These are basically 3D infinite elements. And whenever we are doing numerical simulations, we have to consider the damping of vibrations. So the damping of vibrations basically have two aspects. The first one is the geometric damping, and second one is the material damping. So in this, since we are considering a 3D model, basically it will automatically consider the geometric damping, because whenever there is a vibration and the vibration is traveling to a farther place, the vibration wave actually expands. So whenever there's an expansion of the wavefront, there is a damping. So when we are considering a 3D model, we're already considering the geometric damping, but we have to additionally input the material damping for different layers. So for this, if you refer the textbook of Chopra, there is an equation for the C value. So this C basically comes from the degree of motion, the equation of motion. So in the equation of motion, we have mx double dot plus cx dot plus kx is equal to 0. And that cx dot, that C is represented by this. This is that C. And C is the damping. So this damping is actually having two components. The first component is mass weighted damping, which is alpha. And the second one is stiffness weighted damping. And then if you refer to the literature, these are taken from different literatures. So I just summarize so that if someone wants to apply this, they can directly substitute the equations for this. So the alpha is calculated from this equation and beta is calculated from this equation. The omega is the angular frequency, and then zeta is the damping ratio. So we have equations for estimation of these as well. So omega is the angular frequency, mode of natural frequency. And from this, we compute the value of omega 1 and omega 2. And in order to find out the natural frequency F1 and F2, these are very rough empirical equations. So from these, the Vs is the shear wave velocity, H is the thickness of the layer. And in order to estimate the shear wave velocity also, we are having an equation. So whenever we are in this table, you can see that we are having the E value, that is, we know the elastic modulus, we know the Poisson's ratio, we know the density. So in this equation, we can estimate the shear wave velocity using these three, and this can be substituted to the equation of natural frequency. The Vs is substituted, and H will be the thickness, and then omega is the natural frequency. Similarly, there are equations for the damping ratio as well. It's again based on the same E, nu, and H value. So once you know this, you'll be able to find out the stiffness, and then you will be able to substitute all this in this equation to find out the value of damping. So this is the actual simulation which we are considering. And in this, just imagine that this is the railway track of 30 meters length from the left to the right. And in this, we are taking the data at the central data measurement location. So out of this 30-meter track length, we are considering a vertical section where the data is being quantified, the vibration data is quantified, and this vibration data is recorded at different depths. So the top shows the railway embankment with different strata, and the bottom one shows the natural ground which is supporting this embankment. And whenever a train wheel is passing from the left side to the right, we are continuously taking the readings. So this S value actually represents the eccentricity of the wheel load from this data measurement section. So when the passing wheel is exactly on top of the data measurement section, the eccentricity value is 0. If the train wheel is at a location of -3 meters before reaching the section, it is considered as a trailing eccentricity. And once this wheel load is passing this data measurement section, it is considered as a forward eccentricity. So when we are considering the train wheel is at a trailing eccentricity, it is approaching the data measurement section, and it reaches S is equal to 0, and then it passes to the forward eccentricities. So we are continuously taking the readings of vibration when a train wheel is approaching, when a train wheel is vertically on top, and a train wheel is passing away from the data measurement section. And this measurement is considered at different depths in the ground and also at different distances on the surface level of the ground. So these results will be explained in the future slides. As I mentioned, this is the numerical model developed in Abacus. And if you're considering the data measurement section, the left figure shows the vertical points in which the data is being recorded. So these black dots are represented by these red dots. These are the same. So till this level, you can see that till this level, it is the railway embankment, which is supported on the natural ground, and the natural ground is surrounded by infinite elements. So in the vertical direction, at every layer in the embankment, we are quantifying the vibration levels. We are quantifying the vibrations in the ground at different depths, as well as at different distances on the surface level of the ground. Because if a structure is standing, say, at a distance of 10 meters from the track, we should be able to find out what is the vibration reaching the foundation level of the structure. So for that, we are also considering the horizontal data measurement points in this. So the black graph shows the vibration levels when the wheel load is exactly on top of the data measurement section. And then the other graphs are for the different positions. So I'll just explain in this slide. So what we observed is that when the passing wheel load is vertically on top of this data measurement section, when S is equal to 0 meters, the vibration levels are maximum at different points. And then the vibrations are second highest after the passage of the wheel load to the forward position, and the vibrations are the least before a wheel is reaching the data measurement section. So vibration is maximum for S is equal to 0. Then the higher values are for the forward eccentricities, and then the higher values are for the trailing eccentricities. So these are the different graphs for different eccentricities. So this one is for S is equal to 0. The plus ones are shown for the forward eccentricities, and the cross ones are shown for the negative eccentricities. So you can see that the maximum is for s is equal to 0, followed by forward eccentricities, followed by the trailing eccentricities. If you need to see this for different train speeds, you can refer this paper. And this slide was for the different layers in the embankment. So you can see that these are the vibrations in the sleeper level. This is in the ballast layer. This is in the sub-ballast layer. This is in the subgrade layer, and this is in the embankment fill layer. So these are the different strata in the railway embankment. And this one shows the vibrations in the natural ground which is supporting this embankment. And again, you can see that the vibrations are almost higher in case of s is equal to 0, followed by the forward eccentricities, followed by the trailing eccentricities. Trailing eccentricities, you can see that the value is much lesser compared to the, these are the different vertical depths from the top of the railway track. And this graph is shown by this. So with increase in depth, there is a reduction in the vibration. So this basically means that the vibration is maximum at the ground surface level. And when you go at higher depths in the ground, the vibration actually reduces. And this graph shows the vibration levels in the case when the vibration data is quantified in the horizontal direction, which is the ground surface level. So this graph shows that this is the one which is actually shown in the graph. So with increase in the distance from the, this is the track center line. So with increase in the distance from the track center line, this is how the vibrations will be reducing. So you can see that maximum vibration is at track center line, and the vibration actually reduces when there is an increasing distance from the track center line. You can see that in this graph, the maximum vibration is at the track center line, and it starts reducing, and there is an increasing distance in the ground surface level. And the previous slides were for a single wheel, but in reality, the train has multiple wheels passing. And this graph actually shows the vibrations which are quantified for multiple train wheels. So whenever multiple train wheels are traveling, these are the different vibrations which are being recorded in the different strata of the railway embankment and at different depths in the ground. And for this, we have actually considered the bogie configuration. So bogie basically means this portion. The train wagon actually consists of two bogies. In this section, this is a train wagon. It consists of two bogies. Bogies means it is an assembly of the wheel sets, and each bogie has two axles. There is a wagon. This wagon has two sets of bogies, and each bogie has two wheel sets. So in general, in the BD30, it's actually a train running in the Norway. So we have taken their bogie specifications because this train is actually designed to run with axle loads up to 30 tons. So this suits our design analysis. So we have taken specifications from them. And these are the different values. So you can see that the vibrations are actually increasing. And this graph actually shows when the first wheel set, this actually shows the different positions of the first wheel set. The x-axis actually shows this is the first wheel set. And when this wheel set is at this location, these are the vibration values. And once this first wheel set starts passing through a distance of minus 15 meters to plus 15 meters, that is a total of 30 meters, then this is the increase in the vibration level. And after carrying out the numerical simulations, these were our inferences. So while finding out the vibration levels, we actually took the measurements in all the three directions. So the vibration has components in the vertical direction. It has a component in the lateral direction. It has a component in the longitudinal direction. So we are taking an average of all the three values to find out the PPV. There is an equation for PPV. So from this, what we observed is that the vibrations are maximum in the vertical direction. So the PPV is the peak particle velocity of the ground will actually have its direction in the vertical direction. And another observation was that if you're considering a building standing at farther distance from the track, at the foundation level of this building, both we are considering a point much away from the railway track. Say a building is standing and it has a foundation resting on the soil. At that point, the vibration will have components which are equally dominant in the vertical as well as horizontal directions. That is the reason why we experience horizontal sways in the buildings. And as I said, we observed that the vibration influence zone is a distance of 30 meters beneath the wheel load. So when a train wheel is passing, the vibrations created by those wheels are traveling to a distance of 30 meters beneath the railway wheel. And it was observed that the vibrations in the railway embankment and the ground will decrease with increase in depth. So the maximum vibration is at the top level, and when we are going deeper in the ground, the vibration levels start reducing. And also the maximum vibrations are felt when the wheel load is located exactly on top of the location of interest. So for example, if you're considering a point in the site, when the passing wheel load is located vertically on top, at that point, the vibrations will be maximum. And again, in the ground as well, we can see that with the increase in depth from the ground, the vibrations will start attenuating. And again, in the embankment, what we observed is that a vibration of almost 2 mm per second actually remains even after the wheel load is passing a distance of 15 meters. So in this graph, you can see that when the wheel load is passing a distance of 15 meters, again, almost say 2 mm per second of the vibration remains in the ground. So even after the passage of a train, still we will be able to experience vibrations. That is the reason why. And this vibration is actually having a value of 2 mm per second. And we also observed that in the ground surface level, the attenuation of vibrations will be lesser compared to the depth. So with respect to the depth, the reduction in vibrations are higher. With respect to the horizontal surface level, the vibrations will gradually decline. And as I mentioned, when we are quantifying the ground vibration levels, we also need to find out the frequency with which this vibration is actually occurring. So whenever we have to mention this to an expert, we have to mention that the ground is vibrating at this much velocity at this much frequency. So in order to find out the frequency, what we do is we have the time history of vibrations and we convert this using FFT, that is fast Fourier transform, and we convert the time signal to frequency spectrum signal. So for this, actually, since we are considering time scale less than 1 second, we are doing zero padding as well as hand windowing. So more details about this is presented in the paper. I'll share the details. So we are doing the signal condition using hand window. Hand window is basically considered in the case you can see that it starts from 0, it increases, and when it comes down, it's not actually again touching 0, right? It's having some residue. So what we do is when we do hand window, we force this signal slightly to the 0, so that whenever we are doing FFT, we will need to repeat this same time signal n number of times. So this time signal will be repeated so that each time signal will be continuous. It will increase, it will decrease. Next signal will increase, it will decrease. So to make a continuous profile, we make use of hand window. And zero padding is for considering the exact frequency of vibration in hertz. And this is a sample. So this was the time history of vibrations in the subballast. And then when we do an FFT, this is the frequency scale. So this scale actually is for time versus the peak particle velocity. This is for the frequency versus the peak particle velocity. So the time signal is converted to the frequency signal. What we observe is that the peak frequencies are mostly in the range of 90 hertz. And then there are subdominant frequencies. You can see that there is a peak. This peak is the dominant frequency. And then there are other different small peaks, which are the subdominant frequencies. So we're considering the top 5 dominant frequencies here. And we can the one which is highest. So this mentions that 96.93 is the dominant frequency. And then there are subdominant frequencies. This is the second one, third one, fourth one, and fifth. So I'll just summarize this one in a table here. So the FFT was done using software SIGView. This is a signal spectrum analysis software. And then these are the different dominant frequencies of vibration we observed in different railway embankment strata. So F1 is the dominant frequency, and these are the subdominant frequencies. And one thing what you can observe is that the dominant frequencies of vibration are mostly in the range of say 85 to 95 hertz. So you can see that it's having a value of 85 to almost 95, 97 hertz. And the subdominant frequencies can go up to frequencies like 200 plus hertz. This is in the scale of hertz. So hertz means 84 hertz means the ground will vibrate 84 times a second for different lateral distances from the ground surface level. So basically we can see that most of the vibrations have a dominant frequency in the range of 90 hertz. So we can say that for the Indian railway track conditions, if a train is passing at very high speeds, dominant frequencies of vibration will be around 85 to 95 hertz. And then in the limited to 100 hertz, but you can see that there is a drop in frequency up to below 10 hertz. You can see that at a lateral distance of 10 meters, the frequency drops up to 9 hertz. Then there is 6 hertz. So you might think that higher frequencies of vibration are more serious, but it's not like that. Even lower frequencies of vibration have their own demerits, because you can see that earthquakes. So earthquakes are actually having vibrations, say 1 to 4 hertz. So, but they actually cause a lot of destruction, right? So whenever we are having low frequencies of vibration, and when we have the fundamental frequencies of vibration of buildings in the same range, it will cause resonance. So what resonance is? When the natural frequency of a building and the incident vibration both are in the same frequency range, then there is a movement occurring in the building. There will be a shaking, severe shaking in the building, and this causes distress to the residents who are staying inside. So this is the reason why we are trying to stop the vibrations from reaching a building, so that the building doesn't undergo any vibrations. So we can see that from this table, we can see that the vibrations are going below 10 hertz. See, we are having values of 9 hertz and 6 hertz. So in most of the high-rise buildings, fundamental frequencies usually fall in the range of 1 to 5 hertz. So in our case, when we are having such vibrations reaching the foundation of a building like this, then the incident vibration and the natural frequency of the building both will be the same, and this will cause resonance in the building, causing severe sways in the building. So we need to stop this. And study where which we have conducted to find out how we can reduce these vibrations. So this is the same railway track model we have used for finding out the ground vibrations, and in addition, we are modeling a trench. So this trench is infilled using EPS geoform. Geoform is something like the thermocol we have. So you can see the picture here. There are two types of geoform. One is EPS geoform and one is XPS geoform. EPS is expanded polystyrene, and there is XPS, which is extruded polystyrene. So for our purpose, we are using EPS geoform, and we are trying to find out how we can reduce the vibrations passing from the track onto the structure which is standing away from the railway track. So vibrations are created in the railway track. It passes through the ground, and before reaching a structure standing away from the track, we are trying to reduce these vibrations. So that's why we are putting a trench in between. The right side figure, we can see this. So there is the railway track here. There is a trench just beneath the railway track, so that it will reduce the vibrations passing here. So in addition to the previous analysis, after putting a vibration barrier, we are trying to find out what are the reduced values of vibrations observed here. In the first study, we know what are the vibrations passing. In the second phase, we are putting a barrier, and then we are trying to find out what is the reduction in the vibrations at surface level. So as part of the study, we are trying to find out how the properties of this trench itself will be reducing the vibration levels. So the four different parameters we are considering is first, density of the geoform. So the density of geoform is a material with very less density. So we have densities from say, we are analyzing densities with 15 to 25 kilogram per meter cube, which is much lesser than the soil. So the density of the geoform is one factor. Second, this location of the trench. So this trench can be near to the railway track, and the trench can be away from the track as well, near the structure. So how the position of the trench will affect the vibration is also study guided. And I have taken this from his work. And these are the different rates of geoform we are considering. EPS 15 means the density of geoform is 15 kilograms per meter cube. We are also considering EPS 20, EPS 25. So from this three, we are trying to find out the impact of geoform density on the reduction of vibrations. And these values are estimated from the empirical equations provided by Gade and Dashaka. And here, what we have observed is that these are the 4 graphs showing the impact of density, impact of the distance, impact of the depth, and impact of the width. So I will explain all the 4 graphs. The first graph shows the reduction in vibration. So you can see it is the vibration with lateral distance away from the track center line, and this is the peak particle velocity. So you can see that when there is no trench, when there is no vibration isolation trench, the vibration is maximum. And when you are using densities, geoform with higher densities, the vibration is still higher. And when we are using geoform with lower densities, we are able to reduce the vibrations much efficiently. So from this, we understand in order to reduce the vibrations, the density should be low. And then this is the graph for the depth. So when there is no trench, this is the vibration levels, and these are the vibration levels for different depths. So we can see that it's not much changing, but we can see that when the depth is lesser, the vibration levels are high, and with an increase in the depth of the trench, we are actually able to efficiently mitigate the vibration levels. So you can see that in this graph. So from this, what we understand is that the depth of the trench should be high, and then the third one is the distance of the trench from the track center line. So imagine that the trench is located close to the railway track. In that case, what we observe is that the overall reduction in the vibration is higher. So from this, and from this graph, what we observe is that the width of the trench should be higher. So B stiff is the buffer stiffness. So buffer stiffness is defined as the ratio of the modulus of the geoform material to the thickness of the trench, thickness or the width of the trench. It is E by T. So E by this T is the width of the trench. That is the buffer stiffness values we have computed. And from this graph, we understand that we have to provide geoform infilled trenches with higher width. So the density of geoform should be less, the depth of the trench should be high, the width of the trench should be high, and the distance of the trench from the railway track should be lesser if we want to reduce the vibrations. And again, that was for a single wheel analysis, and these are the different graphs for multiple wheel analysis. And this is just a summary of the previous graphs. So we can see that the trench depth should be high, the trench width should be high, the density should be low, and the distance of the trench from the track should be low. So what we observed is that when we are using EPS 15 geoform with a trench depth of 3 meters and a trench width of 0.5 meters, we are able to attenuate the vibrations by almost 53%. So imagine that if you're having a PPV of 10 mm per second, you are able to reduce it to 5 mm per second. So it's almost half the vibrations. So this is regarding the reduction of vibrations. But one another aspect we have to consider when doing this analysis is that whenever we are putting a vibration isolation trench, there is a reflection of vibrations. So how does this vibration get reduced here? Whenever the vibration is passing, when you're putting a barrier in between, what happens is this barrier will reduce it, right? But how does it reduce? It will actually absorb some vibration, and it will actually reflect some vibration. So this, what the trench does is the trench will reduce it and it will transmit the wave. But how it reduces is that this will actually absorb some, and it will also reflect some vibrations back. So what happens is when this trench is located close to the railway track, what happens is these vibrations go back to the embankment. So the structures which are standing close to the railway track will be saved. But what happens is the railway track itself will experience higher levels of vibration. So in this study, we are trying to find out the impacts of all the 4 properties of the trench, and we are trying to find out how this will affect the reflection of the vibrations. So this figure shows the reflection of the vibrations. You can see that an incident vibration hits the trench, and this vibration is reflected back into the railway embankment. So it is putting a vibration barrier is good for the structure standing outward, but it is also detrimental to the railway embankment structure. So we are trying to find out how much deterioration that is caused, and these are the different results we have obtained from the analysis. So first, what we observe is that when the density of the infilled geoform is high, so when we are using EPS 25 geoform, the reflection of the vibrations is high. So this black colored graph shows the vibration level when there was no trench. So this is the vertical depth in the rail base. So we have an embankment depth of 3 meters, and these are the different values for the sleeper, ballast, sub-ballast. So these are for the different layers. And you can see that when we are putting a vibration railway track itself. So if you're considering this case, you can see that there is an almost at the sleeper level, you can see that there is an increase of. So whenever we are using geoform with higher densities, the reflection of vibrations is more. That is, it is more problematic. When the depth of the trench is higher, again the reflection is higher. And then the third factor is the distance from the track center line. So in this, what we observe is that when the trench is located close to the railway track, then the reflection of vibrations is higher. So the distance from the track center line is less. In that case, the reflection of vibrations will be high. So it should be such that the vibration levels should not be much. If you see the impact is lesser. But again, what we see is that when the trench is located close to the railway track, the vibrations will be higher. And then regarding the width of the trench, when we see this, what we observe is that when the width of the trench is lesser, again the vibration reflection is higher. So if you're installing trenches with higher width, then the reflection will be lesser. That should be our preference. And again, these are for the multiple passing wheels of a train. And these are the vibrations recorded in the different layers of the embankment. So the first one is for the sleeper vibrations. Second one shows the ballast vibrations. This is the sub-ballast, subgrade, and the embankment fill. And the two graphs are represented. The bottom one shows when there is no trench. And in this graph, the red one shows when we are putting a trench at a distance of 10 meters from the track. So we can see that there's a slight amplification of the vibration levels in the railway embankment. I think this is a summary of the previous graphs what we discussed. So amplification of the embankment vibrations is something which we don't really want. So also higher in the case when the trench width is smaller, as well as when the distance of the trench from the railway track is also less. And what we observe is that if you're considering the installation of an EPS 15 infilled geoform trench and with a dimension of 3 meters depth and a width of 0.5 meters, what we observe is that there is an amplification of vibration in the sleepers by 10%. There's an amplification of 8% in the ballast, 7% in the sub-ballast, and in the layers, that is the subgrade and embankment fill which come below the sub-ballast layer, the amplification is almost 5%. And to summarize this, I won't be discussing more on the results. So in our study, what we tried to do is, first, we were trying to find out the wheel load which is being transferred from the train onto the track, and we made use of the software ANSYS to do this. And we had quantified the vertical contact pressure as well as the traction stresses. The second phase, what we did is we tried to quantify the vibrations which are generated due to these loads. And these vibrations were quantified in all the three directions, which is the horizontal directions as well as the vertical direction. And from that, we computed the peak particle velocities of vibration. And then once we have the peak particle velocities, we are converting the time signal to the frequency signal to find out the frequencies of vibrations. And this is done using FFT. Once we know what are the vibration levels, we have made use of EPS geoform as a trench infill material so that we are able to reduce the vibrations which are traveling from the ground onto the structure. So these trenches are installed in between the railway track and the sensitive structure so that the vibrations which are propagating to the sensitive structures are reduced. So in our study, we have tried to find out the efficiency of EPS geoform. There have been previous studies using different materials like rubber tire mixtures and then open trenches. So what we have seen is that open trenching is the most efficient method, but open trenching is not always possible in the field, right? Because if you're having a trench of 3 meters depth, we cannot simply keep it open because someone will fall into it, right? So we cannot simply keep a trench open, and also the trench might collapse as well because the walls of the trench might not stand. So in case of cohesionless soils, what happens is the trench will collapse. So we have to infill the trench with a suitable material which is able to absorb these vibrations. So in our case, we have made use of EPS geofoam for this. So this is the summary of my keynote lecture. I would like to thank everyone for their valuable time.
Now people will appreciate the amount of work which goes into making big infrastructure projects possible.
Yes, sir.
A lot of research is required, a lot of analysis is required, and it is not a simple thing. So we all want high-speed railways and all good facilities, but I think now definitely the civil engineers who are the people who make all these facilities, at least now we have many people who can appreciate this. So you have really impressed upon the people the kind of work, the hard work which goes into this. I'm sure that the people will have many things to ask you.
Thank you, sir.
So thank you, sir. Thank you, Dr. M. Roshan Khan. It was a wonderful session regarding the topic geodynamics of high-speed railways. I hope everyone enjoyed it well. Now the floor is open for the discussion. So those who have any doubts or clarifications regarding the session can type it in the chat box. And I also request the participants to fill the feedback form which is uploaded in the chat box. So, sir, we can wait for 2 minutes for the questions. Sir, I have one doubt, sir. May I ask?
Yeah, please.
Sir, how did you decide this is the optimum location for the trench, sir? How you come to know that you have told that due to the reflecting wave of the geofoam, it will be reflecting back to the track itself, embankment itself. So how did you decide what will be the optimum location for the geofoam trench?
Yes, so this is a very good question actually. So this is even what from the track, or you can save the railway track itself. But the railway track is should be designed so that it will be able to take the augmented loads. So when we're the structure which is standing away from the track in our hands, right? But we can construct a railway track which will be able to take higher loads. It's generally designed so that it will be able to take higher loads. So from our study, what we observed is that when this trench is close to the railway track, it is able to save the structures away, but it will be having higher reflection of vibrations to the track itself. So it should be should be case specific. So in case if you're having a sensitive structure away from the railway track, you will have the liberty to put your vibration isolation trench at a higher distance from the track. But in the urban scenario, if you see, you don't have much space. So there are structures standing just close to the railway track. In that case, what you have to do is, you don't have an option, you have to simply construct it just next to the track. So there is no option in that case. So an optimum section would be such that there is lesser reflection back and there is higher attenuation of vibrations passing away. So there is no single optimum value, but from our section, what we studied, what we found is that a location of 10 meters will be optimal. That is case specific for the tracks.
Okay. Sir, there is one question from Srikantan sir. According to you, what may be the approximate distance from the high-speed railway track to construct a moderate residential building to be constructed in loose sandy soil?
This distance should be a minimum of 15 meters. That is what we observed. So from our analysis, what we found is that the vibrations will travel a distance of 15 meters from the track. So 15 meters will be ideal. case of this loose sand. 15 or higher.
ഓ ആ വീണ്ടും സ്റ്റാർട്ട് ചെയ്യാം.
Sir, there's a question. Any other material can be used as infill for trench isolation, sir?
Yes, there are a lot of materials. So one another aspect is that you can also make use of materials like the sawdust. You can make use of bentonite. You can make use of. You can also keep the trench open. If you are able to do that, that is the most efficient method. But as I said, in case of loose sandy soils, you cannot basically keep it open.
And also, sir,
You have
one
to
more question.
rubber tire mixes. So nowadays you can see that a lot of research is being conducted on scrap tires. So you can make use of make use of the tire chips as a material for this. You can mix the tire chips with sand and you can infill that. In some places, you can also see that sand is also used as an infill material. In some places, in places where there is no sand, and when we have to infill the material, when we have to infill the trench using locally available material, we go for sands also. Sand also has excellent damping properties. Sand in itself is a damping material, but again, there are much better materials like EPS geofoam is a very potential material because you can see that it's having stiffness comparable to soil. So in the long term, it will be able to take the lateral loads acting on the walls of the soil.
യൂട്യൂബിലിട്ടേക്ക്.
Oh yeah. So another thing, what I would suggest is a lot of research can be done on this.
Okay, sir.
That's right. Like you can
Sir,
conduct studies on scrap tire mixtures.
sir, another question from Suman Bhatt. Can this technique be used when there is a high groundwater table?
Do you mean the infilling of this trench?
Yes, sir. Yeah.
Yeah,
This
it can be done. Yeah, it can be done. But in that case, what you need to do is you will need to provide anchors. So you can provide lateral anchors, which will keep the geofoam layer in place. So what happens is, in case there is no support for this, what happens is the geofoam layer will be subject to buoyancy. It will be having uplift forces. So in order to keep this in place, you can provide lateral anchors for that.
Okay, sir.
Sufficient, but it also depends on the exact vibration levels. So one thing I would like to actually highlight is that in our study, we are considering that the railway track is in perfect condition. We are considering that there are no deformities in the railway track. There are no deformities in the actual train itself. So the deformities can be of two types. First, it's just like when our car is falling into a pothole in the road. So a normal car is running. Whenever you're hitting a pothole, your car will be feeling a vibe, right? Actually, when there is a deformity in the track, the deformities could be something like the hanging sleepers, and then there might be n number of track defects, and also there are defects in the train itself. Like there will be wheel flats. So whenever there is a wheel flat, there will be increased levels of vibration. So in our case, the vibration what we have estimated is for ideal track conditions. In the reality, there might be track deformities, there might be structural deformities in the train. So this will lead to increased levels of vibration. In that case, this 15 meters will not be sufficient. That may be the reason why the MBR is actually specifying a distance of 30 meters to be safe. But in the reality, it might not be always practical, considering the limitation of spaces available in the urban cities, the urban scenario. It's very difficult to get those setbacks.
So one more question. Is the design of the existing railway buildings
What we are following is like code. In it, they have mentioned that the buildings should be constructed this much far from the location of the railway track. But in India, I do not think so. Because if you go to cities like Mumbai, you can see that people are staying just next to the railway track, not even a setback of say 3 meters. People are simply constructing structures just next to the track. So I don't actually understand by what the existing railway buildings mean. Are you specifying about the the railway stations? If you went to the railway stations, please stopping. If you're seeing the major railway, the trains will stop there. So when the train speed is lower, the vibration will be lower. So in that case, the buildings should be fine. And you can also see that some stations, the train will not stop. It will simply pass. But the rule is that whenever a train is passing a station, it will reduce its speed. So whenever a train is passing, mostly the locomotive driver is actually given a signal to reduce the train speed. And once the station is passed, they will increase the speeds. In that case, actually, when the train speed is lesser, it should not be an effect. There will be an effect, but it will not be deteriorated.
Okay, sir, one last question. Is there any relation between vibration isolation and liquefaction potential of subsoil material?
Both are actually entirely different things. So liquefaction is actually, in liquefaction, what is actually liquefaction? So liquefaction is actually happening when we are considering a vibration coming from beneath the ground, right? Excitation is in the vertical direction, and then the ground surface level, the soil will be liquefied. But in our case, the loading is entirely different. So these both should be, won't go in the same line. That's what I think.
Okay, sir, thank you very much. Now I call upon Mrs. Geeta KG, Assistant Professor, Civil Engineering, Mes College of Engineering, to deliver the vote of thanks.
Hello, sir. Am I audible?
Yeah.
Respected and our distinguished speaker, respected HOD, my colleagues, participants, and students. Good morning, everyone. It is an honor for me to express my gratitude to everyone present on this day. On behalf of Department of Civil Engineering, Mes College of Engineering, Kuttipuram, I feel immense pleasure to propose a vote of thanks to our eminent speaker, Dr. S, where he discussed clearly the wheel rail load transfer, how the soil movement and vibration occurs, why the vibration need to be incorporated at sites, and explained the mitigation of downbound railway vibrations using EPS geoforms. Really, the session was much informative. Thank you, sir. Thank you very much for the interesting and fruitful session.
Thank you, ma'am. Now I request Dr. Syed Jalaluddin Shah, Professor and Head of the Department Civil Engineering, Mes College of Engineering, to conduct the second session. Welcome, sir.
Okay, I welcome you all to the second session of the day. The session is on geotechnical and environmental engineering. We have 5 papers to be presented in this session. The first paper is titled A Study on Theories of Plasticity and Their Applicability to Soils under Environmental Engineering.